Hello. In the topic number 18, we are going to learn a derivation for total electric field and pattern format of two isotropic point sources. Two isotropic point sources of same amplitude. So here the amplitude is same and opposite phase. So if you see my previous video, we have discussed two isotropic point sources array with same amplitude and same phase. But now we are discussing about an array with opposite phases. So if there are two point sources, a very similar diagram as we have done it earlier, from the center of the coordinate system at a distance of d by 2, there are these 2 point sources, source number 1 and source number 2, but this time their amplitudes are same. The field radiated by them have same amplitude but opposite phase, and we are measuring the total field radiated by them at a distant point in the free space, which is called at a far field, and we are doing this measurement in counterclockwise direction phi. So this is phase phi in the counterclockwise direction, and we are measuring this field at a distance of r. So this is our y-axis and this is x-axis. So as we discussed earlier, these 2 point sources, since they are placed on two opposite sides of this axis, this is on positive x-axis and this is on negative x-axis, and the measurement is being done on positive axis side, there will be definitely difference in the time at which these fields will be measured. So from source 2, the field will be measured, which will be advanced by a factor dr by 2 cos phi, very similar to previous case, and from source 1, the field will be measured, which will be retarded by a factor dr by 2 cos phi. Let me tell you the difference between advanced and retarded. This is the only difference in the time at which these fields are received. The advanced field will be received earlier, and the retarded word here is used to indicate the field received at a later time. So source 2 we represent advanced field, and source 1 we represent retarded field, where dr, as we mentioned earlier, is the distance in radians, which is actually this total distance d in meters multiplied by 2 pi by lambda, which becomes beta d. So dr is measured in radians. Now the total electric field at a large distance r in the direction of phi will be given as E total is equal to the field due to source 1 first, which is E0 e to the power, okay, let's write the field from the source 2 first, because it is positive, because it is advanced, plus j psi by 2, and let us write these two fields separately. By source, this is by source 2, this quantity, and here I'll write the field by source 1. So by source 1, the field radiated will be E0 e to the power minus j psi by 2. E0 is the magnitude of the field, and e to the power minus j psi by 2, where psi represents the phase variation. Psi in case of source 1 is retarded by dr by 2 cos phi, so minus sign, and psi in case of source 2 is advanced, so it is plus j psi by 2. Now the big question is, when we are finding the total field. In previous case, you might have seen we had a plus sign here. That is because both these sources were having same phase. But now the statement says that we have two sources with opposite phase. So opposite phase indicates that these two terms will not be added now, but they will be represented by a minus sign. And this minus sign brings the change in the further steps in the derivation. As you can rewrite this equation, rewrite above equation by taking E0 term common from both these terms, multiplied by 2, and then in the bracket the subtraction of these two terms, E0 e to the power j psi by 2, it is plus j psi by 2 minus, sorry, this E0 is not there, we have already taken it common outside the bracket, e to the power minus j psi by 2 divided by 2. Now the term inside the bracket by trigonometry indicates that it is a sin psi by 2 term, where, let me write what is psi first, where psi is from this dr by 2 cos equation, where psi is represented by this dr cos phi term, dr cos phi. So it is actually psi by 2. We have written here psi by 2. Psi is dr cos phi. So let's write the representation, trigonometric representation of this term in the bracket. So the total electric field, E total, will be now this whole term is nothing but j sin psi by 2. So let's write that j term here, 2j E0 and sin psi by 2. Anyway, we are going to make this term equal to 1 because we consider the maximum field. So since normalization results in 2j E naught equal to 0 is equal to 1, sorry, 2 is equal to 1, and the term remaining now, E total, will be cos of, you can see the term here, not cos, we have sin now. Okay, the cos term will come later when we substitute the value of psi. So now it is, you can see the equation once again here. What equation we have obtained? The equation we have obtained is 2j E naught sin psi by 2. This represents j sin psi by 2. J we have taken outside with 2 E0 term, because we are going to make this whole term equal to 1 when we normalize. And what remains now only is sin psi by 2, where psi is dr cos phi. So there is a cos phi term also, which will come later. So now it is sin psi by 2. Since psi is dr cos phi, the total electric field radiated by an array of two isotropic point sources of equal magnitude or equal amplitude but opposite phase is given by, if we substitute this in this equation, it becomes sin, in place of psi we put this value as dr by 2 cos phi. This is our final equation for the total electric field of the array. Now in case of radiation pattern generated by this antenna, we need to consider certain parameters in this equation. Like, we should know what is the value of phi first. We can take different values of phi from 0 to 180 or 0 to 360 degrees, but there is a slight modification in this analysis compared to the previous case, where we take specific values of phi in order to compute three parameters of a pattern. You know, in a pattern there are three terms we find. we find maxima, which we call as a major lobe. Then we call minima, which we represent by side lobes or back lobe. And then there is another very important term called as null. So to find the maxima, minima and null of the pattern from this electric field radiation pattern equation, we need to do some additional substitutions. So let's do first the analysis by taking the value of dr, as we assume d, the separation between these two elements, is lambda by 2. This is purely an assumption. We are assuming that d is lambda by 2. You can take any value you want. You can take lambda, as I mentioned earlier. You can take lambda by 8 also. The separation between two point sources can be any value, but we take it lambda by 2. So if we take d as lambda by 2, our equation for dr in radians is 2 pi by lambda into d, which makes this 2 pi by lambda into lambda by 2 equal to pi. So our equation modifies, this equation modifies to E total equal to sine, in place of dr we have pi by 2 cos phi. So this is our equation, the final equation for a total electric field when the distance between 2 point sources is lambda by 2. Now let's find out maxima, minima and null one by one. For maxima, there is a small substitution, and this is a value which is computed by experimentation. It is not any mathematical analysis. It is through experimentation it is found that for this particular array, if you want the maxima value, then the term inside this bracket, inside this equations bracket, which is pi by 2 cos phi, is to be, I write 3 cases separately now. For a pattern, for a radiation pattern, we need first the direction of maxima. So for maxima, the term inside the bracket pi by 2 cos phi need to be plus or minus 2k plus 1 pi by 2, where k is representing numbers from 0 to infinity. If we take the first value for k is equal to 0, if we make this term 0, then what we get is pi by 2 cos phi will be equal to plus minus, this term is 0, but this plus 1 remains, and then pi by 2 as it is we get. So if we cancel pi by 2 with this pi by 2, then we have cos phi is equal to plus or minus 1. So you can see here, if you have cos phi is equal to plus minus 1, which is possible for two different angles of phi, that is at 90 degrees, that is at 0 degrees, and since it is cos, it is not sine, it is one possible at 0 degrees and 180 degrees. So at 0 degree or 180 degree of an axis or a coordinate system, you have maxima obtained. Now for the second case, which is representing the null directions, we have assumption pi by 2 cos phi value need to be plus or minus k pi, where k is again ranging between 1 to infinity. So if you take first value for k equal to 0, then cos phi would be 0, which gives us phi for two different values, plus and minus 90 degrees. So you can see the null can be obtained in plus 90 degrees and minus 90 degrees direction. Now the third point we considered is side lobe. But instead of computing side lobes, it would be more beneficial if we go for compute, because side lobes, there is no radiation happening, which is intended radiation, what we say. Whereas the most important point to compute in a radiation pattern is half power beam width. So in case of half power beam width, this substitution for argument cos pi by 2 cos phi is plus or minus 2k plus 1, and now it is pi by 4. If you remember, in case of maxima, this substitution was plus 2k plus minus 2k plus 1 in bracket pi by 2. Now it is plus minus 2k plus 1 pi by 4, and that is for HPBW, half power beam width. So again, this k is ranging between 0 to infinite. So for one value k equal to 0, the value of phi we obtain by substitution in this equation. If we put k is equal to 0, we get here plus minus pi by 4, and then we have pi by 2 here. If we do simplification, you can see the answer that we get is plus minus 60 degrees and plus or minus 120 degrees. So to summarize, the radiation pattern of this array of two isotropic point sources with same magnitude but opposite phase, then we have seen we get maxima in the direction of 0 degree and 180 degree. We get null in the direction of plus or minus 90 degree, and we get HPBW in the direction of plus or minus 60 degree and plus or minus 120 degree. So with the knowledge of these values, we can plot the radiation pattern for this point source, this array of point sources, and the radiation pattern looks like a pattern with a broader major lobes, and the major lobes, as we see, the maxima values are in 0 and 180 degree direction. In the direction of 90 and minus 90, or this can be 270 degrees, plus minus 90 degrees is null, is representing null. This is representing maxima, and we have HPBW here exactly at 60 degrees, plus or minus 60 degrees. So this total HPBW for this case will be 120 degrees is the value of HPBW. So in case of an array of two isotropic point sources with same magnitude but opposite phase, we get broader major lobes, and you know, if area of major lobe omega A is broad, it gives a lower value of directivity, because directivity is defined as ratio of 4 pi to omega A. If this value is large, then definitely the directivity will be small. But in this case, this type of array is termed an Endfire array. So the arrangement with this kind of structure is named as Endfire array. So in this video, we have seen a structure of Endfire array radiation pattern. In the previous video, we had seen the similar radiation pattern with two elements placed. They are having equal magnitude and same phase. But now in this case, they were placed on the axis, but they were having opposite phases. The distance between the two elements was same. 2 point sources was D. So with equal phase, we get broad side, and with opposite phase, we get Endfire. So these are two very important arrays types. So in the next video, we are going to put more focus on these two types of arrays. Thank you.